This conference will now be recorded.
So very good evening students. Today we'll be learning one of the applications of diode, PN junction diode. So that is, what is that application? Application is the rectification. We can use PN junction diode as rectifier. We'll learn it, what is a rectifier and all those things. And finally we'll take a few numerical example based on the concept we have learned so far. Basically with the diodes, PN junction diodes. So the process of converting alternating signal into a direct signal is called rectification. So what is rectification? Rectification means the process of converting excuse me the process of converting alternating signal means it can be current or voltage into a direct signal is called rectification, and the device we use for this rectification is called rectifier. Okay, rectifier is a device which can convert alternating current in or alternating voltage into a direct current or direct voltage. So that is a simple definition of a rectifier circuit or rectifier device. So the diode, you might be remembering that an ideal diode, in case of forward and reverse bias, what we have seen, suppose this is an ideal diode, sorry, this is an ideal PN junction diode. Ideal means what? Ideal means in the forward bias, see, this is the forward bias when we connect the P junction or the P side of the diode with the positive terminal of the battery, and N side we connect with the negative terminal of the battery, then the diode is forward bias. Okay, now if it is it is an ideal diode, in case of forward bias, the junction, you remember, I hope you remember this depletion layer. You remember those mechanisms, how junction diode works. So this junction, PN junction, in forward bias provides almost no resistance in case of ideal diode. So resistance provided by this junction will be ideally zero, and then current will flow in the circuit, okay, in this way, P to N current will flow. And we have seen the diode characteristics or IV characteristics of a PN junction diode. You look, there will be threshold voltage, after that there will be gradual increase in the voltage. In case of forward bias, there is increase in current with increase in voltage, and it has current of the order of milliampere. But if you look the reverse bias, what is reverse bias? If you just make the opposite polarity, you just make it negative and this as positive. Okay, that means an N side of the PN junction diode is connected to positive terminal of the battery and P side is connected to the negative terminal of the battery, then in that case, this junction or the depletion layer will provide almost infinity. In case of ideal diode, infinite resistance, and in that case there will be no flow of current, ideally no flow of current or zero current will flow. So you look, current is only flowing P to N but not N to P. This is not allowed. Only current is flowing P to N. When it is in forward bias, then only it is conducting. Okay, so when we use this PN junction diode in any circuit, in ideal case, if the diode is forward bias, it will conduct, otherwise it will not conduct. That means it has a special property such that it allow flow of current in a single direction or only one direction. This property of diode is called, so diode allows current to flow through it in one direction only, P to N, and this property of diode is called unidirectional property. Unidirectional property. You might be thinking, sir, there is current in the reverse bias also. Why do you say there is no current, zero current? See, the current here of the order of microampere. This is actually, if you go for any practical application, this microampere current is of no use. That's why it is as good as zero current. Okay, so that's why we consider that diode in ideal condition or ideal diode can provide or conduct only when it is forward bias. Okay, in the reverse bias it does not conduct. This property is called unidirectional property, and this unidirectional property can be used to make rectifier, to device rectifier. To make a device rectifier, we can use this diode. Okay, now look, AC signal, we represented AC signal by a sinusoidal curve. You can take cosine or sine curve, anything. Suppose this is a voltage, AC voltage. Okay, this is an AC voltage which changes its direction as well as its magnitude. You look, up to half cycle it has positive value, and see, next half cycle it has negative values. Okay, next half cycle it has negative values. Okay, so if we apply this AC voltage to this diode, actually look, if we apply AC voltage to this diode, what happens? See, in first half cycle it will be positive, this terminal P will be positive, and see, and next half cycle P will be negative. Okay, that means a half of the cycle can be like will make the diode conduct, and negative half cycle diode will not conduct. Okay, so this is how, at least for the positive half cycle, we will get some signal. Okay, we'll discuss those things in detail, so you can at least guess some or get some idea from here itself, that since positive half cycle and negative half cycle make this like this junction diode either forward bias or reverse bias. Because of that, like one half cycle, in one half cycle there will be signal or there will be flow of current, and the negative half cycle there will be no current, no flow of current. So this is the property we are going to use to make this AC signal a unidirectional signal, okay, or alternating signal to DC signal, okay. And there are two types of rectifier circuits, okay. There are two types of rectifier. One is half wave rectifier, that means only half of the alternating signal will be rectified in the sense converted to DC, and full wave rectifier when both the signal or both the cycles can be converted into DC signal, okay. We'll now discuss this half wave rectifier and full wave rectifier, like what are the necessary circuits, how it works or working principle, and what will be the output waveform. These are the things we are going to discuss today. So half wave rectifier. So what is a half wave rectifier and how it works, we'll discuss now. First of all, let us take this circuit diagram. This is called circuit diagram of a half wave rectifier. Half wave rectifier. Okay. So what are the necessary circuit components we require to make a half wave rectifier using diode, PN junction diode? So what are the necessary components? You need a transformer. First of all, you look, this is the transformer. So this is primary coil, this is secondary coil as denoted over here, and the primary coil is connected to the AC mains here, AC mains, okay, AC mains, okay. And the terminals of the secondary, like A and B terminals of the secondary, they are connected in series with diode. See, series with a single diode, PN junction diode, through a load resistor. That means the two terminals of the secondary coil is connected to a diode, and along with that there is a resistor in series, and that's how the circuit is complete here. Now look what happens. Now we'll see what is the working principle. So here, before we discuss working principle, we consider the diode to be an ideal one. What does that mean? We have discussed already. Ideal diode means in forward bias there will be flow of current, and in reverse bias there will be no flow of current, or zero current will flow through the diode. So that is what ideal diode means. So yeah, so that is what ideal diode is meaning. Now what is the working principle? Suppose an AC signal is fed to, see, an AC signal is fed to primary coil of the transformer. When AC signal is fed to this primary coil, there will be change in the signal. So there will be change in the flux, and that change in the flask will be linked with the secondary coil, and that's how the same secondary voltage will be induced here. Now we have already learned transformer can be step down, step up, etc. But the frequency of the signals will be the same. Okay, in the primary and secondary. That's what I can say. But the peak value may be varying according to your requirement. You can use the number of turns and get the induced voltage more or less than primary voltage in the output terminals of the secondary. That is not our concern today. So what is our concern is that the same AC signal is induced at the terminals A and B of the secondary. When we feed AC signal to this primary of the transformer, same AC voltage will be same in the sense that it has same time period and frequency. That's what I wanted to mean. So AC signal will be, or AC voltage will be induced to secondary. Okay. Now that AC signal, as I was discussing in the previous slide, that AC signal has, suppose I take sine curve. So it has positive half cycle as well as negative half cycle. Okay. Or sorry, negative value and positive values. So in the first half cycle, suppose it is positive. So the value of the voltage is positive. See this one in the first half cycle. So in the first half cycle, what will happen? The A will be positive and B will be negative. Okay. First half cycle, A will be having positive value because this here it will be A and this will be B. So B will be negative. That means this diode is, see, this side is negative and this side P is positive. Okay, connected to positive terminal of the battery. That means what? This is forward bias. Okay, forward biased. And when it is forward biased, there will be current flowing through the diode all the way through this load resistor, and this is how the circuit will make a complete flow. See, current will flow in this way, come all the way here, and then it goes like this. Okay, this is how it will flow. So it is fine when it is forward bias. In the first half cycle, A is positive, B is negative, then we get some current. And if we want to calculate voltage, what is the voltage across RL? In fact, that is the voltage we want. We have given input voltage, we are getting output voltage across L, the load resistors. So we can use a voltmeter and get the voltage from here. Okay, now look what I'll do. If I look the second half cycle, that means the B will be negative. See, this second half cycle, this A will be at the negative potential. A will be at negative potential and B will be at positive potential. That means now, how is the biasing of the diode? This is P and this is N. Now this is positive and this is negative. So now it is actually reverse bias. Okay, now it is reverse bias. Since it is reverse bias, there will be no flow of current. Okay, so current will be zero. That's what we'll see here in the circuit. There will be no current flowing, and hence there will be no voltage. No voltage. If we see in the voltmeter connected across the RL, will show zero voltage. So in the positive half cycle you are getting voltage, then in the negative half cycle you are not getting, like other half cycle you are not getting any signal. Okay, so again when the third half like in the like after completing one full cycle, again it starts from positive, so this A will be again positively biased, like A will be at positive potential and this will be B will be at negative potential, again it will be forward bias, further it will be reverse bias, like that it will go on, and see how the output waveform will be. If you look the output waveform, the the output waveform will be something like this. See this is the voltage at A. So when the voltage at A is positive, here it is positive, then it is forward bias, so you will get a voltage across this RL. So that's why this is the voltage. Now in the negative half cycle, when it is negative, then it is reverse bias, so there will be no current. Look, there is no current here, zero voltage. Okay, zero voltage, no voltage. Again, when this A will become again positive, then you will get signal again. Further in the negative half cycle, like when this A becomes negative, then there will be no current again. So this is how you are getting, see, the output waveform. This is the output. Okay, this is the output voltage, this is output voltage, this is input voltage, input signal fed to the primary of the transformer. Now this output voltage is actually exactly same as the only positive positive half cycle. Okay, or positive half cycle. See, this is, so this is how you are getting exactly the output waveform has exactly the form of only positive cycles. Okay, positive cycles. So these two, you can see that these two have actually output has the same frequency, same time period, like see, same period. Okay, same same time period or same frequency as the input signal or frequency, same frequency as the input signal, input signal. Okay, so signal. Okay, so sometimes there will be there will be a question that suppose a 100 hertz AC signal is fed to the primary of a half wave rectifier, what will be the frequency of the output voltage? So in that case, the output voltage also will have 100 hertz frequency. Okay, so I hope you have understood this. And see, the output waveform we get, you might be thinking how it is DC. You might be thinking how it is DC. We are reading rectifier circuit which will convert AC signal to DC signal, but how it is DC? DC should have been a constant line with time. It does not change its direction as well as its magnitude. Magnitude may change, but direction doesn't change. So in this case, see, DC signal means DC signal means it can be either this or it can have only a positive value, but value may change. Doesn't matter. So that is called DC. So in this case, you look here, you are getting the output signal which is always positive, which has a value positive always. It doesn't have any negative value. So this has unidirectional voltage. So it has unidirectional voltage, but this voltage is not a constant voltage. It is a pulsating voltage. So this is called pulse because it is coming out of like as a pulse. So this is called pulsating unidirectional output. You are getting only positive values. That's why it is unidirectional and it is DC. But it is not a constant it doesn't have a constant value like this. It has pulsating voltage. So pulsating unidirectional voltage we get out of half wave rectifier. Okay, so this is the working principle. This is the output waveform. This is the input waveform at A. This is the necessary circuit of the half wave rectifier. Okay, and this output of the half wave rectifier has the same frequency as the input signal. So this is what we have learned from the half wave rectifier. Okay, Deepa, you have any question here? If you have any, you can ask me now. Okay, or else you can ask at the end also. Let us now go to the second part of this rectifier, that is the full wave rectifier. What is full wave rectifier? See here, we can convert half of the AC signal to DC signal. Only the positive half cycle we are able to convert into DC. But what about this? In the half wave rectifier, we could not do this. We could not convert these negative values also into DC or positive, like any DC signal. So half of the wave is actually lost. Only half of the wave is rectified here. That's why this circuit is called, or this use of diode. When we use only a single diode, the rectification happens for half of the alternating voltage or current. So since half of the waveform is rectified, this is called half wave rectifier. Now, why to waste power? Why to waste signal? Can't we make use of this negative signal also, negative values of the signal also? The answer is yes. If we use two diodes instead of using only a single diode, then maybe we can convert both the signals, both positive and negative signals, to a DC signal. Let us see what we do in full wave rectifier. So full wave rectifier, as I mentioned, that the whole wave can be converted into DC signal. Let us see how we do. First of all, we have to understand what is the necessary circuit. So this is the necessary circuit. Here, look here. Also, we need a transformer, but this transformer is a special type transformer. This is called central tap transformer. In the previous case, or half wave rectifier, we have used an ordinary transformer, but in this case we need a central tap transformer. So we need that kind of transformer. What does that mean? It has three terminals. That means that it has three ends. Like see, it has end A, it has end B, and center tap has another terminal. That's all. This is center tap transformer. So primary is as it is connected to an AC mains. Okay, it is connected to an AC mains. Okay, and the secondary has a center tap. This I can give a name as T, the center tap point T. A and B, as it is, we have learned in the half wave rectifier case also. We have learned A and B were there. Now we have another terminal that is called center tap, and that center tap is there with the secondary terminal, secondary coil. This is secondary, this is primary coil. All right. So in this case also, by induction process, the AC signal will be induced across the terminals of the secondary coil. And look, now we have used two diodes instead of using one. We are taking two p-n junction diodes. One is named as D1, another one is named as D2. Okay, there are two diodes. Now see how the diodes are connected. This is very important. You should understand this. You should understand the difference between full wave rectifier circuit and half wave rectifier circuit. See, in the half wave rectifier circuit, we had only one diode. So the two terminals of the secondary had been connected to diode in series along with the load resistor RL. Okay, this is a very simple circuit. Now when we talk about full wave rectifier circuit, here in this case we are using two diodes D1 and D2, but they are actually connected to two different circuits. You can see that. See, this A is one terminal which is connected to P side of D1 diode 1. Okay, and its N terminal is connected to this point which is a common point. Let us say this is common point, because the N terminal or N side of the D2 diode also is connected to this common terminal, this terminal. So that's why this point say common. Okay, but the PR, look, P is connected to A and P side of the D2 is connected to B. Okay, so far it is okay. Now look, there is a central tap point. Okay, central tap point, and this central tap is connected to this common point, that means to the N sides of the diodes through a load resistor RL. This center tap is connected to this N terminals or N sides of the diodes through a series resistor RL. This is called load resistor. Okay, and output will be measured across this load resistor. I hope you have understood this. When we discuss the working principle, you will understand again clearly. Okay, now look what will happen in this case also. When we feed the signal, AC signal, so the A point will be sometime, suppose in the first half cycle, A is positive and B is negative. Okay, first half cycle. So then what will happen? The D1 will be forward bias. Okay, in the first half cycle, D1 will be D1 forward bias. Okay, forward biased. And whereas B is negative, that means B is reverse biased. Sorry, D2 is reverse biased. That means one diode will be forward biased and another one will be negative. Another one will be at reverse bias condition. Okay. So at this condition, what happens? The current will flow through diode D1, but there will be no flow of current through D2. Why? Because this D2 is at reverse bias. Now you might be having a question, then what is the path of the current? How the current is flowing through the circuit? Look, I'll tell you the path. See, it will start from suppose T to A to C the common point, and then X, then through RL it will go to Y, and from Y to again center tap. Okay, so this is the path, the current flow in this way now. Okay, like that it goes through the center tap like that, and it completes the path or completes the circuit. So this is how current. See, since this diode is non-conducting or it is not conducting, so through this current will not flow. Okay, through this current will not flow. So this is a separate path for the current when only D1 is conducting. But anyway, you will get the voltage over here. Okay, you will get the voltage across RL. Suppose that is V0. Okay, so you will get, so this is positive half cycle. So one half cycle you get positive voltage. Okay, now let us see negative half cycle. So in the second half cycle, I'll clean everything. In the second half cycle, A will be negative, this point will be positive with respect to central point, central tap point. Then this D2 will be forward bias AFB, and this will be reverse bias RB. D1 will be reverse bias. So in the forward bias condition, that conducts. That's why only only D2 diode will conduct, but this will not conduct in the second half cycle. Okay, because now this one is at positive potential with respect to central tap. That's why this D2 diode is forward bias, so it will conduct current. And what will be the path or what will be the circuit for the current to flow? See, through the diode it will go in this way up to X, and then through RL, and all the way up to this to central tap. So the circuit, see, it has now like that it will go. So central tap, so I'll write T2, or let me write this as point B to common point C here, then it goes to X, then through RL it goes to Y, and Y to again T. So this is how the current will flow in the separate circuit. See, earlier the current was flowing in this way, during the positive half cycle. Now in the negative half cycle, the D2 diode will conduct, so current will flow in this way, this way, this way, then it will go all the way up to here. So one thing can you notice, even though different diodes are conducting, but the current through RL is in the same direction. Current through RL is in the same direction. That means in both the cycles, during positive half cycle or during negative half cycle, for both the cycles we are getting voltage across RL, and since both of them has the same maximum values, so the same voltage you get. So let me show you the output waveform as well as input waveform. So at A, what is the input waveform? This is the input waveform. So look, only the positive half cycle it will conduct, so D1 is conducting. So due to D1 you will get voltage across RL. Okay, now in the negative half cycle, there is see the waveform of this input signal at B is like this. Okay, that means they are in opposite phase. Okay, the signal waveform or input waveform at A and B are in opposite phase, 180-degree opposite phase. So when it is positive, it is negative, so only the D1 is conducting. Now when the signal is in the negative half cycle, during the negative half cycle, D2 will conduct, because D2 there will be positive potential at the P side of the PN junction diode. So D2 will conduct during the negative half cycle. Then again during positive half cycle, D1 starts conducting. Further in the negative half cycle, D2 conducts. So in the positive half cycle, D1 conducts, D1 diodes conduct, and during the negative half cycle D2 diode conducts. Since both the diodes are conducting and the current is in the same direction, therefore you will get voltage for both cycles. So that's why it is called full wave rectifier circuit, and in this case we have used two diodes. And see, but there is no constant. Now also you are getting the voltage in the same direction, or only one direction, that is positive direction. See, there is no negative values of the output. You have only positive values of the output, but output is not constant. It is a pulsating voltage again. Pulsating output voltage you are getting. Pulsating voltage. Pulsating voltage means it is coming as a pulse, like it goes, like it starts from 0 to maximum, then again 0, again start from 0 to maximum, again comes 0, like that. This is a kind of a pulse, or this is called pulsating output voltage you are getting out of this full wave rectifier circuit. But for each cycle you get voltage. Okay, and see, in this case, you have output frequency. Look, see, during a complete cycle, how many times you are getting output? Two times. So therefore it has output frequency twice of the input frequency. So I'll write it here. So since we are getting two times output, two times in a single cycle, that's why it has actually frequency 2. Okay, frequency twice of the input signal. It has output signal, so output frequency is 2 times the input frequency. I'll just give you a simple example. Input frequency. Suppose the AC signal has frequency 50 Hz, then what will be the output frequency? That will be 100 Hz. Okay, so that is what is the frequency. So there will be a question in competitive exam, kind of this. So when the input signal is fed 50 Hz, then what will be the output signal in case of full wave rectifier, in case of half wave rectifier? So these are the concept about full wave rectifier and half wave rectifier. So we have seen that we are getting pulsating voltage, but DC means, see, if we want to use this voltage or output of the rectifier circuit, then it is of no use if you just turn, like if you just want to glow or lit a bulb with this pulsating voltage, what will happen? It will glow for some time, then again it will be off, again glow, again off, like that it will show. But we generally don't want this kind of pulsating voltage, right? Pulsating signal. So to make it a constant DC signal, we can use a filter circuit. You can see this is a filter circuit. It consists of, so this is actually this is the rectifier. That means this whole circuit over here, this whole circuit is the rectifier here, and then output rectifier is fed to a parallel combination of RC circuit. Look, this is R and C. Sorry, this is, yes, RC. You can even use RL also, inductor in series with resistor. Here load resistance RL, across that, like parallel to that, a capacitor is being connected. So if you provide this pulsating output to this circuit, this particular circuit is called this CR circuit is called filter circuit. This particular circuit will give you a constant voltage. This is a constant DC voltage. Okay, constant DC voltage. DC voltage. So this capacitor will charge and discharge during both, like during charging. See, during when, see this, if this is the pulsating voltage, when the current is increasing and reaching up to voltage is reaching up to maximum during that cycle, that means during the quarter of this pulsating voltage, will this capacitor will be charged, okay, then it will discharge such that the voltage does not fall to zero. It will try to make it constant, okay. This is how filter circuit make this pulsating voltage into a constant DC voltage. I'll discuss this working principle and how it is making a constant voltage out of this pulsating voltage. I'll discuss this in next class in very detail. That means the working principle of this filter circuit will discuss in detail in the next class. But now, let me take you through few numerical example. I'll take very simple problems related to diode. Okay. So filter circuit I'll discuss in the next class. Now we'll discuss few numerical examples related to this chapter, basically with the diodes. So which of the following circuit represents a forward bias? So we have seen when P side is connected to positive terminal and N side is connected to negative terminal, that biasing or that type of biasing is called forward biasing. But sometime you look that, see the C or see the D, it has neither negative, see it has both negative and positive, both side negative and negative, here both side positive. So how do you understand which side, like how is it connected, whether it is forward bias or reverse bias? So when both are having positive at positive potential, then you have to see which one is more positive, which one is more negative or less positive. So in this case it is, see this side is less positive because 5 positive 5 voltage, so less positive. But this side you look, this is more positive 12, so more positive. So by this way also we can understand whether it is forward or reverse bias. So in this case, since it is less positive, P side is less positive than the N side, so this is at reverse bias. Okay, this is reverse biasing. Okay, the diode is reverse biased. Now if you take C, both are negative, but you have to see which one is more negative, which one is more positive, or sorry, which one is less negative. So this is actually minus 5 means it has more negative, right? More negative, and this is having less negative, right? So that means this is also reverse bias. Okay, this is also reverse bias, right? Now look here, it is 0 and this is positive, this is also reverse bias. But in this case this is 0 and this is negative, this is actually forward bias. So this is forward bias. I hope you have understood. When you don't have only positive and negative, you have both positive negative, 0 positive 0 negative. In that case you have to understand, like you have to consider which one is more positive, which one is less positive. If P is more positive than N, then it is forward bias. If P is more negative than N, then it is reverse bias. Okay, so this is how you have to understand. So the correct answer is this one. I'll clean everything. So correct answer will be this, because P is positive 0. 0 actually has higher potential. This is 0 means higher, at higher potential. P is at higher potential than the N side. So that's why it is forward bias. Okay. Now we'll take up a numerical problem with diode. Look here, what is the current in the given circuit? So to know the current through the circuit, you need to know, first of all, you have to take that these diodes are ideal in characteristics unless the voltage across the junction is given. So there is no voltage across the junction is given. Therefore, I'll take that the diodes are ideal diode. That means if the diode is forward bias, then only current will flow, and if the diode is reverse bias, then there will be no flow. Now look, we will see which diode is reverse biased and which diode is at forward bias condition. Look, this one, this is positive, so this positive terminal goes here. That means D2, this P, this is P, this is N. So D2 actually forward biased, FB forward bias. Now this goes here also. This is positive then. So this is positive, this is negative. So D1 is reverse biased at reverse bias. Okay, that's why this will not conduct. So current will only flow through this way. Okay, like this. It will go from positive terminal of the battery, then it will go all the way D2 through this 30 ohm resistance and all the way through battery to 20 ohm, like that it will go. So this is the circuit. So now we have got, see, there is no resistance in ideal case in the forward bias. So no resistance across this or no potential drop across this. Only potential is dropped across 30 ohm and 20 ohm. That is what we will consider here. So what is the resistance of the circuit? The total resistance and total voltage we know. So what will be the current in the circuit? So voltage is 5, and what is the, so V by R? R total resistance, equivalent resistance, these are in series. So equivalent resistance is 50. Okay. So this is the current V by R. So 5 by 50. This, if we make it short, then it will be 1 by 10. Okay, or 0.1 ampere current. Okay. So this is how you have to see. When there is diode given in the circuit, you have to check whether the given diode in this particular circuit is at reverse bias condition or forward bias condition. According to that, you have to solve the problem. We'll take up one more example so that you understand. Yeah, so look this problem. So in this case, what is the current flowing through AB? What is the current flowing through AB? You have to calculate. Now in this case, you look, see, this is at positive voltage and this is negative, but see, you have to see this is what is the voltage across this, you have to calculate. Okay, so just take 2 minutes to think and then tell me how do you do this. Deepa, we have discussed on problem like that. You can check this problem and tell me how do you solve it. Okay, so what you have to see, first of all, what is the potential difference? What is the potential difference? So this is negative, this is positive. So potential difference will be across this is potential difference is, so actually this is a B point. You are asked to calculate the current through AB. So what will be the current through AB? That is what you are asked to calculate. So what is the potential difference? 4 minus of minus 6. So you get 10 volt potential difference. Okay. Now one more point is that what is the, okay, so since it is positive terminal, positive, positive, and this is at negative, so it is forward bias condition. So there is no much to think now. We have understood what is the potential difference across this A and B point. We know the resistance, that is 1 kilo ohm. So you can calculate the current through AB now. So current through AB will be V by R. V is the potential difference across A and B. So that is 10 volt divided by 1 kilo ohm. That means this 10 to the power 3. So this will be ampere. This is ohm. So it will be 10 to the power minus 2 ampere. Okay. So this is the current. So this is how you can solve problem, numerical problems related to diode. We'll take few numerical problems again when we complete this Zener diode, etc. So for today we'll stop it here. Next day we'll learn first the working principle of the filter circuit, and then we'll go to the Zener diode, and there also we'll learn one application of Zener diode, that is voltage stabilizer. Okay, the Zener diode is used as a stabilizer. We'll first learn what is Zener diode and what are the properties of Zener diode also. Then we'll go to the application part of Zener diode. Okay, so we'll meet again on Sunday. So bye for today.